So 1 over r d square d r square r phi plus 1 over r square sine theta d d theta sine theta d phi d theta. And then I have 1 plus 1 over r square sine square theta d square phi d phi square has to be equal to 1 over c square d square phi d t square. That is the governing equation for the waves that can be propagated due to the trembling sphere. Okay. The solution. What would be the solution look like? Before we start to find the solution, we can argue that this term would be 0 because it is a symmetry with respect to phi, right? The velocity and the pressure in phi direction would be independent because it is just oscillating this direction. So therefore, as long as I found the velocity over here, it would be same as the velocity over here because it is oscillating this direction. Okay? Then we can try the solution like this. That will be a function of r and theta. That will be look like anything wrong? Trembling. This is trembling. Huh? Only in z direction. Oscillating in only z direction. Sphere is oscillating with respect to only z direction. With the magnitude u0, I mean with the velocity u0 exponential minus j omega t. Okay? And maybe you asked me why we are studying this special case. Why? Then I ask you why we study this special breathing sphere case. Why? The reason? What is the reason? Our objective is to know how the wave is propagating if there is a structure that is vibrating with a different amplitude, right? Like this, or like this. We want to know. And how can we predict the sound at a certain point? We know that, right? We know the sound magnitude at position r is equal to what? Integration over the surface pressure on the surface. That means I have a surface S0 that is a function of R0. That means I am using coordinate that is R0, and that is R. and dg dr0, g is a function of r0, and minus g r0 and p, no. Okay, g, sorry, r0 and dp dr0, and integration of the surface S0, that is function of r0. Okay, this integral formula provides us the pressure over the surface. Okay, that is Kirchhoff-Helmholtz integral equation. We learned this a long time ago, but I'm sure everybody forgot it already. But this is the time I ask you to remember and understand this equation. Okay? What's the meaning of Kirchhoff-Helmholtz integral equation? No. What's the meaning of Kirchhoff-Helmholtz integral equation? You can speak Korean if you like. What's the meaning? The meaning is that if we know the pressure on this surface, that is a PR0, right? And if you know the velocity on the surface, that is dpdr, right? dpdr0. Okay, if you know this pressure and this velocity, and then if you know this Green's function, then we can predict the pressure at any point. Okay, that Green's function has to satisfy this even homogeneous wave equation, right? In other words, the Green's function is the wave field that would be generated by impulse response at r equal r0. In other words, when I put the impulse at r equal r0, the wave will be propagated, and that is the Green's function. Okay? So this is our objective. Okay? Huh? Okay. Sure.
바운더리에서의 우리가 프레셔를 알면 어떤 쓰레기 상에서는 그 내부의 미니의 포인트에서의 프레셔를 에스티메이션 할 수 있다. 이거 알고 있는데요. 그 경계 조건의 바깥쪽에 있는 어떤 포인트에 대해서 모든 프레셔를 알 수 예측할 수 있는.
Okay. What you knew is a very special case. This is very general case. Okay? Let me explain more. Suppose I have a boundary look like this, and this is oscillating, as you mentioned. Okay? Then I take integration like this on this surface. Okay? And I say this is R0 and this is R. Okay? Then I can predict the pressure inside. Okay?